So before we look at fluid mechanics, I want to give us an introduction to fluid mechanics, okay? And before we talk about fluid mechanics, let's talk about mechanics. What are or what is mechanics? Very easy. I know you have done physics and you have done some subjects in engineering. Now, mechanics is the study of objects in motion or objects that are at rest. Okay, I repeat that. Mechanics is a study of objects in motion or that are moving or objects at rest due to the influence of what? Forces. So I'm saying that the mechanics is a study of bodies that are at rest, or I can say stationary, or moving under the influence of forces. So here is a basic definition for mechanics. All right, very important. So before we start talking about fluid mechanics, we have to understand what each word represents. Now, what is a fluid? Now, a fluid is a substance that can be either a liquid or a gas. So when a substance is in liquid or gas phase, that substance is called a liquid. So I'm saying that here, I'm saying that a fluid, or I'm saying that a substance in liquid or gaseous form or gaseous phase is referred to as a fluid. All right, that is a very important definition for fluid and for mechanics. Now, I want also note that a fluid is a substance that can deform continuously under the action of shear forces. I repeat that. A fluid is a substance that can deform. Now, when I say deform, it means that it can change. All right, it can change due to its density. So a fluid is a substance which deforms continuously under the action of what? Shearing forces. So I can say a fluid is a substance that deforms, yes, continuously under the action of shearing forces. All right, good. Now, we have established the definition for mechanics and for fluid. Now, the question is this: what is fluid mechanics? So now we can say that fluid mechanics is the science that deals with what? With the behavior of fluids, either at rest or what? In motion. I repeat that. So from these two definitions, we can say that fluid mechanics is a science that deals with the behavior of fluids at rest or in motion. Very, very important. That's one. Two, it deals with the interaction of fluids with solids or other fluids. So I'm saying that, therefore, what we are saying is this, that fluid mechanics is the science that deals with the behavior of fluids at rest or in motion. That's one. Also, it deals with the interaction of fluids with other solids, fluids with solids and other fluids at a boundary. So this is a simple definition for fluid mechanics, and everything we shall be doing within the next 14 or 13 weeks is centered around this definition. All right, so all we shall be doing on fluid mechanics is about the behavior of fluids either at rest or in motion, or its interaction with other fluids, with solids, and other fluids. So now I want us to note a very important point, please. When fluids are at rest, look at this. When fluids are at rest, it is called fluid statics. When fluids are at rest, it is called fluid statics. When fluids are at high motion, it is called fluid dynamics. I repeat that. When fluids are at rest, it is called fluid statics. When fluids are in motion, it is called fluid dynamic. Now, let's look at areas where we can apply fluid mechanics. Because I guess you must have think about it. Why am I doing this subject? Why are we doing this? Now, fluid mechanics is very important in every aspect of our industries today. As long as that industry uses fluid, then this is a very important concept that we must look into. Now, I will give us about 2 or 3 applications of fluid mechanics. Then I will want you guys to give me some others. So I want you guys to start thinking of areas in which we can apply fluid mechanics. Number 1, I will give us one. I'll give us one right here. The first area where we can apply fluid mechanics is that we can apply fluid mechanics in the design of heating and air conditioning. All right, it is applied, it is used in the design of heating and air conditioning. All right, your hydraulic brake, look at this, your hydraulic brakes. All right, because some hydraulic brakes use what? They use fluids. It is used in power steering. Okay, because power steering has a fluid. Okay, also it is used in automatic transmission. It is used in automatic transmission. The list goes on and on. Okay, so we use fluid mechanics is applied in air conditioning, is applied in hydraulic brakes, in power steerings, and in automatic transmission, and the list goes on and on. So number 2, it is used in the design of the components of a refrigerator. Okay, now let me explain this. Now, the working fluid of a refrigerator is what? It is what? A refrigerant. All right, what we call gas. A refrigerator uses what? Refrigerants to control the system. And if there's no gas or refrigerant in your fridge, in your refrigerator, it won't work. So a refrigerator uses what? Gas. as its working fluid. And I'm saying that we use the concepts of fluid mechanics in the design of what? The component, in fact, of all the components of what? A refrigerator. That is a very, very important factor that you must understand. Also, fluid mechanics is used in automobile. Okay, you're using what? Automobile, from your fuel pumps, your gas cylinder, your fuel injectors, name them. So number 3, we are saying that it is used in the design of automobile. Yeah. Now this includes what? Your fuel pumps, injectors, your carburetors, and the list goes on. All right, so these are some areas that we can apply fluid mechanics. Now I'll give us a next one. It is used in the, okay, I would say fluid mechanics plays a vital role in the human body. Fluid mechanics plays a vital role in, it plays a vital role in the human body. Okay, so we are saying that fluid mechanics plays a vital role in our airflow, the breathing. In fact, just imagine, look at this. If you look at the heart, our heart pumps blood, not true, to all parts of the body, through the arteries, through the veins, the lungs. All these are concepts of what? Fluid mechanics. Now look at this. If you have seen a breathing machine, or a machine used for dialysis, they all work under the concepts of fluid mechanics. So you see that. So all we are saying is this, that we can use fluid mechanics in engineering, one, in medicine, can be used domestically for our piping, your piping at home, your sewage tank. All of these is, in fact, your ducting. All of these are using the concept of fluid mechanics. So I'm saying that fluid mechanics is a very important aspect of mechatronics and of industrial automation. So if you are doing mechatronics and you are doing automation, you need to understand the concept of fluids. You have to understand how fluids behave. So that is what we shall be looking at in the next 13 or 14 weeks. How fluids behave and how fluids interact with other solids and other what? Fluids. Now let's look at pressure. Let's look at pressure. Now, what is pressure? As you all know, is the what? Is the ratio of what? Of the force over the what? The area. Is that true? Good. Now, when I say that fluids deform continuously, for a fluid to deform, that means there must be pressure applied to it. So when we are saying the fluids deform continuously, we are saying that there is pressure being applied to that fluid. Okay, so in this topic, we shall be looking at pressure and how pressure affects fluids. But also we will look at pressure, which is formula is what? Is pressure P equal to the force over the area. Now this area is the surface on which or over which the force is applied. So we shall be looking at pressure in solving some questions. And please note that pressure is in what? Is in Newton per meters squared. Very important. I hope you guys remember this. And also, please remember that pressure can also be measured in what? In Pascal. Is that true? We can also measure pressure in Pascal. I hope you guys note that. Also, we can also measure pressure in bars. In bars. Very, very important, because we shall be using these units. And please note that 1 Pascal is equal to 1 Newton per meter squared. Very important. And also please note that 1 bar is equal to 10 to the 5 Newton per meters squared. So guys, these are very important conversion factors that we must remember as we continue in this subject of fluid mechanics. So before we continue with pressure, let's look at 3 important pressures that we shall be using in this semester. The first one is called atmospheric pressure. It's called atmospheric pressure. Now, this is a very important pressure that we shall be using in this semester. Now, when we say atmospheric, it means pressure within the atmosphere of Earth. Is the pressure within the atmosphere of what? Of what? Earth. That is called, is the pressure within the atmosphere of Earth. That is called atmospheric what? Pressure, for short. Now, the symbol we use for atmospheric pressure is giving us P subscript A T M. That is for atmospheric what? Pressure. Is what? Is the pressure within the atmosphere of what? Earth. All right. Now, question: how do we measure atmospheric pressure? We can measure this kind of pressure by the height of column of liquid that it can support. I repeat that: we can measure atmospheric pressure by the height of column of liquid it can support. That is one way that we can measure atmospheric pressure. As we continue in this class, we shall look at different ways of how we can calculate atmospheric pressure. And please note that the symbol is giving us P subscript A T M. Now, also, I want us to note, please note that atmospheric pressure at sea level, please note that atmospheric pressure at sea level is about 101.325 kilonewton per meter square. It is, I'm saying that atmospheric pressure at sea level is what? 101.325 kilonewton per meter squared. Kilonewton per meter squared. So that is the value for atmospheric pressure at sea level. And please note that we shall be needing this value as we start solving some basic questions. Let's look at our next type of pressure. Is called the gauge pressure. We have the we have the gauge pressure. Now, gauge pressure, as the name sounds, is the pressure that is gotten from measuring devices. So when I use a barometer to measure pressure, that pressure is called gauge pressure. So it is the pressure measured with the help of a pressure measuring device. I'm saying that gauge pressure is a pressure measured with the help of a pressure measuring device. Yes, that is called a gauge pressure. Now, let me explain. Gauge pressure can be either positive or it can be negative. Look at this, please. Listen carefully. Gauge pressure can be either positive or it can be negative. Now, when is it negative or when is it positive? When the gauge pressure is positive, it means that the pressure is above the atmospheric pressure. I repeat that. When gauge pressure is positive, it means that it is above the atmospheric pressure. When gauge pressure is negative, it means that it is below the atmospheric pressure. All right. So these are ways that we can gauge the pressure of an environment. All right. Now, the symbol that we use for gauge pressure is giving us P subscript G. So it's P subscript G. That's the symbol we use for gauge pressure. Let's look at one more. It's called the absolute pressure. It's called the absolute pressure. We have what you call the absolute pressure. All right. Now, this pressure is normally gotten from a vacuum. If you remember, a vacuum has zero pressure. That zero pressure is called absolute pressure. Now, I can relate this pressure to gauge pressure and to atmospheric pressure. So I can say that this is the sum of the atmospheric pressure and the gauge pressure. So I'm saying that absolute pressure is the algebraic sum of the gauge pressure and the atmospheric pressure. All right. So this is a simple definition for absolute pressure. I can write this in formula form. It becomes, so I can say, and please note that the symbol we use for this is P subscript A. We use what? We use P subscript A. Okay, so we can write out these statements in formula. It becomes P subscript A is equal to P, the gauge pressure, plus P atmospheric pressure. So here is a formula that we can use to solve questions that involve gauge pressure, atmospheric pressure, and absolute pressure. And please, I want us to note, please note that the gauge pressure can also be equal to, the gauge pressure can also be equal to the density times gravity times height. So here is a next formula we can use to find the gauge pressure. This is density. The G here is the acceleration due to gravity, and H is the height. And please note, for this class, our gravity is equal to 9.81 meters per second squared. All right, so here is the very first equation that we are using to solve questions on this topic. All right, let's look at a very simple question here. Very simple question. It says, calculate the pressure gauge of air in a cylinder if the atmospheric gauge is this 101.3 and the absolute pressure is 780 kN per meter squared. We're asked to find the pressure gauge. As always, step 1, I will write out my given datas. So number 1, my pressure gauge is not given, so it's unknown. I'm giving my pressure in the atmosphere is giving us 101.3 kN per meter squared. I'm giving the absolute pressure, which is PA. The PA is giving us 780. It's giving us 780 kilonewton per meter squared. All right, so how do we solve this question? The first thing I do is this. I have to bring back my formula, which is this. I know that my pressure, my PA, is equal to my PG plus my P atmosphere. So we can log in the values and we can get our answer. So we're asked to find the gauge pressure, so I can transpose. I can move this to the side, it becomes a minus, so we have PA minus P atmosphere equal to PG. Okay, so therefore I can say that my PG is equal to my PA. My PA is 780, so I have 780 minus my P atmosphere is 101.3. So we subtract and our answer is 678.7 kilonewton per meter squared. Kilonewton per meter squared. So that is our answer. So this is a very important formula in fluid mechanics. A very important formula. In fact, when we start looking at questions on pressure measuring device, this formula is the key equation that we use to solve pressure involving or pressure measuring devices. Okay, so we are asked to consider a pressure gauge attached to a boiler which is at sea level and showing a reading pressure of what? This is the pressure gauge, because that is the pressure that is gotten from the pressure measuring device. So I can see that my PG is 9 bars. Remember, we are asked to leave our answer in what? In this form. So I can convert these to kilonewton per meter squared. Okay, so that gives me 9 times 10 to the 5 kilonewton per meter squared. Okay, also we are given the atmospheric pressure, so my P atmosphere is giving us 1.013 bar. Again, I convert to kilonewton per meter squared. So that gives me 1.013 times 10 to the 5 times 10 to the 5 kilonewton per meter squared. It says we're asked to find the absolute pressure. So I can say therefore my absolute pressure is equal to my gauge pressure plus the atmospheric pressure. All right, so what next? I log in my values. So I have my gauge pressure is 9 times 10 to the 5 plus for the atmosphere is 1.013 times 10 to the 5. So we can add this together. When you add this together, you should get 1001.3 kilonewton per meters squared. So that is our answer to this question. Now let's talk about fluid properties. Now I was saying that fluids include gases or liquids. Now fluids has different characteristics. For example, gases are light and compressible. I repeat that. Gases are light and compressible, but liquids are heavy and incompressible. Liquids are incompressible, while gases are compressible. So the first property here is called the mass density. I call it mass density. The first one here, I call it the mass density. Yeah, mass density. Now, what is mass density? It is the ratio. It is the ratio of the mass to the volume. Is the ratio of the mass to the volume. So the symbol we use for mass density is written as this. Look at this. That's a symbol for mass density. The formula is mass density is equal to the mass over the volume. The next property we have for fluid is called the specific weight. It's called the specific weight. Specific weight. It's called the specific weight. Now what is this? This is the ratio of the weight per unit volume. It is the weight per unit volume. Look at this, guys. It's the weight per unit volume. And please don't forget that the symbol we use for density is what? Is kilogram per meter cube. Okay? Now, the symbol we use for the weight is, we use what? W. Alright? W. The formula is this. The formula is W is equal to the weight over the volume is the weight over the volume. And please note that the units for specific weights is given as Newton per meters cube. Please don't forget this. Don't forget this. Now, I can break down this equation further. That means we can say that weight is equal to what? Is equal to mg over the volume. All right. I hope everyone is seeing the screen. Now, you can see that mass over volume is what? Is density. Okay? So therefore, I can say that my specific weight is equal to density times gravity. So here is a formula we use for specific weights. The next one we have is called specific gravity. The reason I'm doing this is that we shall be seeing all these again in this semester. We have what we call specific gravity. Now, what is specific gravity? Is the ratio of the weight of the substance to the weight of water. Is the ratio of the weight of the substance to the weight of water, or of an equal volume of water. So I'm saying that is the ratio of the weight of the substance to the weight of equal volume of water at 4 degrees Celsius. At 4 degree what? Celsius. So this is a simple definition for specific what? Gravity. The symbol we use for specific gravity is given as what? Is given as S. The formula is this. The formula is S equal to the weight of the substance, okay, over the weight of water. The weight of water. So it's the weight of the substance over the weight of water, or we can say is the density of a substance over the density of water. So these are the formulas we have for specific gravity. We have one more, and that is called the specific. It's called the specific volume. Okay, we have one more. It's called the specific volume. Now, what is this? This is the reciprocal of mass density, or we can say is the ratio of the volume to the mass. It is the ratio of the volume to the mass. Or I can say it is the reciprocal of mass density. Okay, it is the reciprocal of mass density. And please note that the symbol we use for specific volume is given as common V. Common V is the ratio of what? Or I can say is the reciprocal of what? Mass density. All right, and you know that is equal to 1 over what? Mass over volume. When we transpose this, we can say that the specific volume, small v, is equal to what? The volume over mass. Please note that this v here is for volume. The v here is for volume. So these are some properties of fluids. Okay, these are some properties of fluids, and as we continue in this semester, we shall be looking at how these properties can affect the fluid. Okay.